So if you remember from last time, we were actually talking about file systems. And this is a classic one. This is the multi-level indexed file inode from BSD Unix 4.1. And if you remember, this was a header format that had been built basically to optimize for small files while at the same time allowing large ones. And so, basically the way that optimization worked was a series of direct, single indirect, double indirect, and triple indirect blocks where the direct pointers point directly at data blocks, the single indirect points at a block of pointers, and so on. And the net result of this and the fact that blocks were 1K back then meant that this, the maximum file size was about 16 gigabytes. Okay? The pros of this were that it kind of had everything in one inode, so it's relatively simple. The inodes are small so that you could actually put multiple of them in a block, and that's an optimization that gets used. And small files are really cheap, up to 10K. And everybody see where I got 10K from? 10 times 1K, right? The downside of this format by itself was really that it didn't guarantee anything about performance. Basically, all it did was it guaranteed that you could find the blocks of interest, but you needed to do something else in order to get performance out of that, and that was all about 4.2. So what did they do in 4.2 to get performance out of this very data structure? Anybody remember? What were some of the optimizations? How do you get this thing to be fast? Yeah. Say again? So never let the disk get full. So how did that help? Well, not quite. So disk full is a good sort of secondary thing they did. But what was the disk full actually buying them? Yes? So the real key here is to try to keep blocks to be contiguous. And so by never letting your disk get 100% full, it was more likely there were a bunch of blocks that were next to each other on the same track, for instance. So yeah, so was the ultimately what they did was they had that 10% number, never let it get fuller than 90%. As a result, they were able to be more likely to get a bunch of blocks next to each other. Okay, is everybody with me on that? There was other optimizations that they did. Does anybody remember? So the big one is make sure the data blocks are as close to each other as possible. What was another optimization? Just seeing if you guys were listening last time. Yeah. So the skip sectoring, yeah. So the idea there was don't put your blocks on the next to each other on the track because you want to allow a little time for the software to process a block and ask for the next one without losing performance because the disk just turned beyond the block you really wanted. So that was good. What was another one? What about the inodes? Yeah. Yeah, store files in the same directory near each other. They put inodes in cylinder groups so that there were inodes plus the directory plus the files all together on similar tracks. So those were all about locality. And the thing that I want you to get out of this is that was a performance optimization on top of this structure. So this structure gave them the flexibility in file size, and then when you put the optimizations on top, you most of the time got good performance. But it didn't have to be perfect in order to make the file work. Whereas in Demos, kind of the file size was tied to whether you could find big chunks or not. Okay, so this was kind of a nice optimization or nice division of labor. There was the correctness of what the file looked like, and including its maximum size, and then there was the optimization, which mostly gave you good performance. And that's a good division to keep in mind for future systems you might design. Were there any other questions on this format? Okay. And then this is what we just said, right? So 4.2 had the so-called fast file system. There's a paper up there about what the FAST file system did, you might take a look at that. But here are just the things that we talked about. Basically try to find big holes so that new files are likely to be able to grow without running into other files. Put the inodes in cylinder groups rather than at the beginning of the disk. Store files in the same directory near each other, and so on. And this actually went further because you get clustering, automatic defragmenting. I'm going to mention the Linux file system in just a second, where they also introduced things like extents, which were, rather than allocating things on a small block basis, you allocate big chunks all the time, and that was another way of getting performance. Okay. So today I want to finish up file systems to some extent and talk about caching and so on, and then we're going to talk about durability and how to make sure that your files are around. And this is going to be a two-part conversation. Today we'll talk about how to make sure your files are still around locally, and then in a week or so we'll talk about very distributed storage systems where the files are durable because you spread them in China and in Europe and all over the place, and therefore it's unlikely that a single point of failure is going to destroy them, other than perhaps thermonuclear disaster, which at that point you probably don't care whether your files are there anymore. So, okay, so here is Linux, which is a very popular system, as you're well aware, and seems to be creeping into the mobile space with Android and so on. And this is the file system, which is called ext2, and the extension ext3 with journaling. And what you find out about this is, if you look very carefully, for one thing, the inode structure is almost identical with what was in 4.2 or 4.1 BSD. The only thing they did a little differently was there are 12 direct pointers instead of 10. Okay, but otherwise they're still indirect block, single indirect block, single double indirect block, single triple indirect block. So the format's almost identical. Another interesting thing that they did was you can set the block size at the time that you format. So you could ask for a 1K block size if you want, and you'd get stuck with about 16 gigabyte maximum file size. Mostly you get 4K, and that's a pretty common number. And there you get, what, 4 times 16 gigabytes, right? So you get 64 gigabyte maximum file size. Any of you have a 64 gigabyte file stored somewhere? Probably not yet, right? So, okay, so 64 gigabytes is a good upper bound for right now. There's some hardware like the Alpha that actually has 8K page tables and higher, and so you can make ext2 or 3 store even more. And all I wanted to point out about some things that are a little different is they have what are called block groups, which are kind of like cylinder groups, and think of them as a group of tracks or cylinders that are treated together. They each have their inodes that are formatted, and then block group 0, turns out inode 2, for what it's worth, is always the root file system. So when Linux boots, it always knows by finding out where inode 2 is, where the root file system is. And so if you look, and that's a piece of irrelevant information for you that you'll go away really excited about today, I'm sure. But if you notice, so for instance, if we want to make a new file /dir1/file1.dat, notice that we go to inode 2, and we look in the inode structure, and there's a direct pointer to the root directory, which is block 258. See that? And in here, you search down, you find directory 1. And that points you at inode 5033, which it turns out is in another block group in this instance. And here we look up directory 1 by finding it starts at block 18431 and da-da-dum. We look down in here, we find file1.dat, which is inode 5110. Go in here, this starts at block 20,002 and yada, 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 and we've got our file. Now, there you go. That's an actual file system layout. Okay? And the big difference between ext2 and 3 is that ext3 is essentially ext2 plus a journal, and I'll say a little bit about what the journal is in a few slides. Questions? Yes?
Are all these inode lookups actually disk lookups, or are they cache?
Unfortunately, a lot of these inode lookups are disk lookups initially, but once the inodes get cached, then they could be cache lookups. So both answers, yes?
So say, file1.dat is two different block sections, where would it end up be, or if it was in two different groups, for example?
If it's so, the blocks and the inodes are all named uniquely, so you can easily spread things across block groups. It's just that they try to keep them within a block group. You get better locality that way.
Yeah.
Good. Yeah. Well, ext4 adds, so ext3 sort of forces you to flush some things out, whereas ext4 lets things as higher performance, and it does rearrange things quite a bit. And so ext4 typically is a higher performing file system, but it's a little bit maybe less secure from a data standpoint than ext3. Not a lot, but a little bit. Yeah. So it's a little easier to get into some cases with ext4 where you lose your data. Riser, Riser is yet another file system. It's close. I mean, we could talk about it offline if you want, but I mean, Linux being a free software sort of view of the world, or the open software view of the world, tends to have a zillion file systems even, which is kind of fun about it, although mostly people end up using ext2, 3, and now 4. The other big thing about ext4, by the way, is all of the pointers are a lot bigger, and so you can handle 64 terabyte partitions if you want to, where you couldn't do that very well before. Or actually, let me take that back. You can get up to 16, no, yeah. You cannot do, I don't think you can do 64 terabytes with ext3, so that's another big thing. It gets up there. Okay. Any other questions? Okay. So, good. Now, we'll talk about journaling in just a second, but the other thing about ext3 is there are several different levels of journaling which you can invoke, which they trade off performance for reliability, and we'll see what that means in a little bit. So, I want to finish up a little bit here some of the notions of caching, and one of them is, so there's a lot of in-memory data structures that are part of the file system, which you've touched upon a little bit. So, for instance, what happens when you open a file? Well, in user space, you call the open system call, and what does that do? Well, typically associated with your process is a directory, is a bunch of things that are in memory, and that open typically has to load the directory into memory so that you can look things up and you can find out where the inode is, and then you can pull parts of the directory structure and so on out. All of that stuff is cached. So when we were talking through, you load this and you load that, you load that, those pieces are all pulled into memory and cached as part of the process. And the thing that's good about that is that different users who are accessing the same files don't necessarily have to pull the inodes in multiple times if they haven't changed. So there's both per process and system-wide tables that are involved here. So the per process table has a set of file handles, as you're well aware. So every process has a unique file handle table starting at, what's the first file handle? Well, there's 0, 1, and 2, right? What's 0 and 1? Standard in, standard out, and 2 is standard error. And then starting from then are the actual file handles for the process. Well, what does the kernel do with those numbers? It looks them up in a table. Okay, and those tables are basically, you basically say, well, read from the file handle. You look that file handle up in the per process structure. That gives you a handle to a system-wide table, so that if two people have the same file open, which you guys might remember, then there's one entry in a system-wide table about that file with a count that says how many people have it. So in particular, if you remember this, if you unlink the file and one of the people that has it closes it, it's still around till the last person closes it, and then it goes away. And that's all tracked in these in-memory structures. Okay. So let's talk about caching. So it shouldn't surprise anybody that caches come up again. All right, we could probably rename this class the caching and a little bit of other operating system stuff, right? Because haven't we run into caches the whole term? So what happens in this case, both the name translations and the data are cached. We just talked about inodes being cached. Those are disk blocks, but they're, in general, not just the inodes. All of the blocks are cached. So if you open a file and you read it, close it, and then you open it again and read it, you'll find it's a lot faster the second time. Why is that? It's been loaded into memory already. It's been cached. Okay? So let's talk about the name translations for a moment. So those obviously are the case where I walk through the directory inode structure to resolve the components. And so back here, remember, we looked at this. This was, look up the root directory, then look up dir1, then look up the file. That stuff is all cached so that the next time somebody looks up a file, it doesn't actually have to traverse all of those blocks. Okay, now the downside of that cache is that you got to make sure it stays consistent. So the moment somebody changes or renames a directory, you got to go in and flush the cache out. So in general, caching having to do with the file system, so this is both name translation and disk blocks, are cached in what's called the buffer cache. Now what's the buffer cache? Well, the buffer cache is DRAM used for caching things about the file system, which is different from DRAM used for virtual memory. Okay, so you've been with project number 3. You're dealing with DRAM that is part of the virtual memory system. Page fault, pick a DRAM page out of the clock algorithm, link it in, so on. Right? That's what you're doing. This is different DRAM that you've set aside, and it holds blocks. It holds name resolutions, okay, and both for performance reasons, so that when you read the same file twice, you don't actually have to go to the disk, and for helping basically run the elevator algorithm. So when you write data, it goes into the cache, not on the disk, and therefore the disk driver can decide when to write back blocks such that it sort of picks a good ordering of the elevator, of the head motion, and in some cases it's going to wait long enough, hoping that if you open a temporary file, write it, close it, delete it, it may not even have to go back to disk. Okay, so if you think about your /tmp directory that you have on a Linux system, when you write things in there, if you delete them quickly enough, they may never actually go to the physical disk. Okay. So what's the replacement policy on the buffer cache? It's LRU. And in this case, we can actually do some sort of linked list or timestamps or whatever to get real LRU. And so the advantages of this buffer cache is it's very great for name translation. It works well in general as long as the memory is big enough. Here's a great example where it works poorly. So does anybody recognize what this command does? Anybody gotten sophisticated enough with find to ever try this? So this actually runs the find command starting at the local directory, and at every file that it locates or directory, it actually executes the following command: grep foo, and this 2 braces actually means the file name, and then \semicolon is part of this syntax. And so this command actually walks through all of the subdirectories starting at the local one and greps for the word foo. Okay, this is probably the most useful find command I ever learned. Okay, I don't know if anybody ever tried this before? Yeah. Isn't that a great command? Yeah. So now the problem with this command is it walks through every file and every subdirectory. What is that going to do to your buffer cache? Well, every file and every subdirectory is going to get loaded into the buffer cache, which isn't going to be big enough. And so what happens is this particular command is guaranteed to flush out any data that's in your buffer cache and be useless from a caching standpoint. Okay? So, everybody see that? So there's no way that you're going to have enough DRAM to cover the whole disk, for instance, if you do this at the top. So what are some other replacement policies than LRU? Well, you could imagine that an application gets to request another policy. Like, for instance, find might say, I'm only going to use each file I touch once, so don't bother caching it. Or if you cache it, don't kick anything else out. Just use, compete with a chunk of cache you've left for me. All right. Question? Yes?
If you call the flush command and you have a buffer cache in place, you execute the flush system call,
Yes.
is that going to reduce the kernel life, or is it potentially still going to spin?
No, so the flush command is precisely to flush out data that might be in the buffer cache. So as you can probably see, if dirty data is in the buffer cache, we have a problem because if the system crashes before it actually goes out to disk, then we lose the data. Right? So this seems like a pretty serious reliability problem. Okay, good. Any question? Yes? So great. So where is this buffer cache? This buffer cache is DRAM, and it's managed entirely by software. And so then the question is, how big is it? Suppose I've got 4 gigabytes of DRAM in my system. How big is the buffer cache? Okay. Have I given you enough information to answer that question? How do we know how big it can't, if we can't exceed what? 4 gigabytes. In fact, in the old days, what systems would do is, as a compile time option in the operating system, you would say this amount of DRAM is for the buffer cache and this amount is for the virtual memory system, and it was a hard boundary. Today's systems try to actually dynamically switch between the virtual memory system and the buffer cache. What this means, though, is if you start reading huge files, you could actually end up kicking things out of virtual memory, because you need more buffer cache. And so it tries to make your buffer cache bigger, which means the memory available to your programs are smaller, and things page fault a lot more. Yes?
So is modern operating systems also aware of the memory that might be between the DRAM and the disk?
Like?
For example, the newer technologies that are coming out, phase change and RAM, these things that they are now using as part of caching.
I would say that so things like phase change memory and flash are new enough that it depends on whether you have a driver that's aware of them or not. Usually what happens with those is there's actually a file system that's built on top of them that's custom. Using them kind of in between DRAM and the disk is not as common as you might think yet. How much should be allocated? Well, this is too much memory. The file system cache can't run applications at once. Too little memory in the file system cache, and everything goes to disk, and the cache is pointless. And so basically, modern systems do this dynamic adjustment, but obviously it's not perfect. I just gave you a command, namely that find command, which is likely to overfill the buffer cache and kick things out of virtual memory. Okay, so this is not a perfect system. Now, another thing that's kind of cool about having a buffer cache is you don't have to do all of your reads to disk on demand. So for instance, suppose you read 2 bytes in a file. What happens? Well, obviously, it's got to read at least 1 block, correct? Where does the rest of that data go? The buffer cache. So that when you read the next 2 bytes of data, it just goes to memory. It doesn't actually go to disk. However, we can do even better than that, which is called read-ahead prefetching, which is if you start reading from the beginning of a file, what it'll actually do is it'll read more data than you requested and put it into the buffer cache so it's there when you want it. So the cache now becomes a way of avoiding compulsory misses in the cache. Question? Yes? So the good question, why can't this be part of the virtual memory system? It's a different animal. I mean, in general, you're not really mapping it with virtual addresses necessarily. This is kind of, this is basically a cache for files. Now, in reality, you probably could come up with a way of treating some process is the file cache manager, I suppose, and map buffer cache things into it, or but it's a little bit of kind of a funny twist in the semantics. So basically, we're exploiting sequentiality as being the most common access pattern, and we're making use of it by prefetching. And the other thing that I would point out is once you've got a buffer cache, now in theory, the elevator algorithm can exploit it. It can take all the requests that are coming in and the prefetches and decide how to schedule prefetches and requests so that they minimize the head movement. And this is particularly important on the outside direction, writes, because those dirty blocks get reordered in a way that are going to basically move the head as little as possible. Now, of course, yes? Yes, the prefetching is in danger of kicking other things out of the buffer cache. So, go ahead. Finish your thought. That's a great thought, so keep going with it.
It's just odd to me because, like, from a standpoint of prefetching within hardware, sometimes you'll have like a separate problem for it. So do no operating systems do that?
I would never claim that no operating systems did that, because I'm sure somebody might. But there's always a trade-off with prefetching, which is a great point to bring up, what's called cache pollution, which is you pull in things that kick out stuff you really wanted to be in there. And that's always a danger in prefetching. And as you point out, you could probably set aside some of your buffer cache for prefetching. It's just that the management of that is another level of complexity, and you'd have to trade off whether it's worth it or not. But heck, if you want to go there, you could build a clock algorithm with a separate, separate set of prefetch blocks that sort of work their way back into the clock algorithm as they're used or something. I mean, you could do all sorts of interesting management of this. Okay. So of course, how much do you prefetch? Well, this is just hitting on that question that was just raised. Too many prefetches, you get delays on requests by other apps. Think about that. If I'm asking for a bunch of prefetched blocks and somebody else needs blocks right now, I'm wasting disk time prefetching. And so you got to be very careful about that. And of course, if I don't have much prefetching, then I can end up with many seeks. The easy way to think of that is you've got two processes that are both reading at different parts of the disk. Okay, if I don't prefetch properly, then the head is going to be going back and forth to satisfy those reads. On the other hand, if I do a really good job of prefetching, then the head's going to be moving a lot less rapidly. Okay, so there's a lot to be said here for prefetching for optimization of use of disk. I think that was all. Okay, any questions on that? So I just wanted to point out that there's yet another type of cache in the system. I don't think I've ever tried to count the number of different types of cache available in this class, but there are many. So then finally, I want to mention this dirty data thing, which is Ash, go ahead. So for a solid state drive, there's sort of less of an advantage to prefetching because it's faster to get the data. There's two reasons they might still prefetch. One is I'm just using the algorithms unmodified, and it doesn't really know that it's not a real disk. And that actually is more likely than you might think, because most solid-state drives, well, I'll talk about this in a couple slides, but most solid-state drives are hidden behind an actual disk interface, so the operating system may not even know it's a solid-state disk. The second reason you might do that is again, there's a little bit more latency to get at behind those interfaces than direct DRAM in most cases today still, and so you might want to prefetch to get rid of some of that latency. It's a good question. So let's talk about delayed writes. So I said this already, but I want to just point this out again. So when you write a file, the data doesn't go to disk immediately. Okay? For those of you that think that just because you write data, it's safe, you might be disappointed, okay, if you crash the system. And basically, write copies data from the user buffer into the kernel buffer, and the buffer cache lets you do that. It basically just lets you copy dirty data directly into the cache, and somebody later says, oh, I've got dirty data, let me flush it out. And of course, in order to make this work, if somebody actually tries to read the data before it's written to disk, the buffer cache is transparently going to forward those updated data to the new person. So if you write a file and you open and read it in another process, you won't know whether it's on disk or not. It'll look like it's on disk because the buffer cache is in the way there and it's transparent. Okay, so just because you write something and read it back somewhere else doesn't mean it's safe. Okay? And actually, I want to amend what I said earlier about flush. So flush actually isn't entirely guaranteed to push things out to disk. Actually, what all that flush does is guarantees that it's pushed out from your user buffers into the buffer cache. The only way to get truly flush out the buffer cache is to actually execute what's called a sync system call. Question? Yes.
So, what situations cause the buffer like that dirty data in the buffer cache to actually be written?
So the let's see, do I say this on my desk? So this is basically time. Is the answer to your question.
Or if it like got replaced?
So two things will happen. One is if your buffer cache overfills, then it's got to be written back. And the second is basically there's a time constraint. For instance, in Unix, it says that the data will never be there more than 30 seconds. Okay, so basically, if you write some data and then wait a long time, it will be on disk, assuming you haven't crashed yet. Okay, or if you happen to be really paranoid, you have to become root, but then you could execute sync and it'll go out.
Apply to the file system, or does the single call do things like network ports and video ports also, or
No, sync is just for the file system. And it actually tries to flush out all the file systems. A safe way to reboot is sync, 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 reboot. Just to make sure that it really has gotten out there, although I think probably one sync is enough, but old habits die hard. So the advantages of the delayed write process is, one, the scheduler can efficiently schedule things. And I say this even though I told you that, well, the elevator algorithm's already done by the disk. Why does the OS have to do it? Well, the OS can still reorder things and hand a stream of basically local requests to the disk scheduler if it wants to, thereby making sure, because the buffers that are in the disk are not that big. The disk allocation algorithm, here's an interesting one, can run with the right size. So here's a problem. You open a file and you start writing it and then you close it. Now the problem is, until you close, the system doesn't know how big your file is. But you're interested in making it have great locality. Well, what you want to do is, if you let it get entirely written in the buffer cache, and then you hit close, now the file system knows how big the file is, and it can go look for a chunk of blocks that are big enough to hold the whole file and get the best locality out of it. So by delaying things in the buffer cache, you actually give more information to the file system that wasn't there before, and it can do a better job of allocating blocks. And then finally, this is the amusing thing I mentioned that you probably never realized. It's possible, especially when you're compiling and stuff, for temporary files to get written to /temp and deleted before they ever make it to the disk. And so they're purely in memory. Question? Yes?
Like say, if you kind of write something like gedit, and then you save, is it fully atomic in that when you start saving, all of that will be saved, or like I'm looking at the same file as gedit from another computer?
So no. So if you're saving data out, it's rarely atomic entirely. So it's possible to actually see under some circumstances that a file is partially written if you start reading it too soon. And when we talk about distributed file systems in NFS, several of them actually have this race condition mode where you can see things being non-atomically written.
So if I open like the same file on two different computers with gedit, and I save it, it is like possible that I see like kind of interleaved saves.
It's possible. It's much less likely now with NFS version 4 than it was with NFS version 1. But yes, it's possible to see things be not entirely atomic. It's even possible, in theory, on a local machine, because there's no guarantees of atomicity. So as a process is writing, if you're reading, you can see changed versions, because it's like as a window going out. So you have to know what you're looking for to do these experiments, but it's possible to see these sort of weird conditions that don't quite meet your thoughts of the way a file system ought to work. So you got to be careful. There's a lot of parallelism going on down there. So the disadvantages, of course, of this system, as I've described it, is what if the system crashes before the file has been written out? And you cared about the data. Well, then you just lost the data, and you probably care even more. Okay? So, and here's a great example. Suppose you're writing things out, and the inode never gets written to the disk, but the data does. Well, too bad, right? Because the inode has all the pointers to which blocks are the data. So the fact that the data is on the disk doesn't help anybody. All right, and this is why things like inodes and even directories, which are typically called metadata, are extremely important to save. Okay? Now we'll start talking about ways of getting around some of these problems in a second here, but are there any questions? Now what I want you to realize here is that something like delayed writes weren't introduced because somebody felt like they wanted to screw up users. I mean, it's not like you put in delayed writes because, there'll be some funny failure cases, and won't that be amusing when I read about it in the news? Okay, so I'll tell you that that didn't happen that way. The delayed writes are here for good reason, right? These are performance reasons, and this is a good example where performance and reliability are not always in sync with each other. So how do we fix some of this? So how do we keep some of the advantages of delayed writes, but really have a little more confidence that our data won't get corrupted on a crash? What can we do?
One alternative is to also store it in a non-volatile place as well.
So one option is to actually have flash or some other non-volatile RAM, which is faster than a disk, that you use as a temporary storage spot where you push everything quickly out to that, and then you work it to the disk. Okay, and if you do that in the right way, then if the thing crashes in the middle, at least your data is safe in this flash, and you can recover it. Okay, that's a good option. What else? Yes. Right. So one option would be very aggressively write. Okay, so you don't delay write. You actually just write. Yeah. Okay, good. So you pick metadata out of the picture and you write it. Okay. Now the only problem, that sounds good until you realize the following. Suppose you write the inodes out, but the data never makes it to disk. And now you go look at the inode, now you got garbage, right? So the fact that your file was 43.6 bytes long or 43.6 kilobytes long is great, but there's no data there to actually recover, right? So, there are people that actually consider that a better failure mode than complete corruption, because the rest of the system's probably still okay, but if that's your data, you're probably not happy. Okay, so we'll get to that in a second. So Administrivia, as you're well aware, so we don't have midterm 2, but we do have a final. Yeah, DOE. Yeah. So this is about it's a little more than a month away, so it's getting there. Believe it or not, our last official class is December 1st, which is the Wednesday after Thanksgiving, so it's getting close. Basically, you're responsible kind of for all the material from the class, although we'll bias it a bit toward the second half. Okay? You get 2 sheets of notes, both sides, handwritten, no magnifying glasses, no microfiche, and you can reuse your notes from the previous exam if you wanted to. I'm not going to prevent that. Okay, any questions on the final? So obviously anything up till the last day is fair game for the final. Now, what is not fair game for the final, but is here for fun, is actually they're an optional final lecture. So I've allocated this class during the R week. So that's Monday the 6th. And this is basically, a free lecture of whatever topics you find interesting. If you send them to me and I get enough interesting topics to put together a lecture, then we'll have one. I haven't heard anything from too many people yet, but you could ask about real-time operating systems or secure hardware. Or I've even had people ask about quantum computing, which I've done lectures on in my final lecture. They've asked me about dragons occasionally, since that's a favorite topic of mine. They're not really mythical, they're out there. Whatever. So send me mail about things you might want to talk about. Presumably it has something to do with OSs, although you can see the quantum computing and maybe the dragons are a little far astray, but that's okay. I've had people ask me, Windows versus Linux. That was a few years ago. Whatever. Any questions on that? So this will be totally optional. Nothing that I talk about will be on the final. It's the Monday after the last class, and it's going to be here at the same time, and we'll just sit here and ask questions. How many people would come to such a lecture? All right, good. Yeah, we kind of, I can just see myself lecturing to an empty room. Well, so Kubi, what do you think? Well, okay. You're all coding for Project 3, right? This is a challenging project. I would say it'd be good to get going earlier rather than later. This one has some complex cases because the interaction between the clock algorithm and processes swapping in and out are sometimes tricky to debug. So I would say get your first version. If you had your first version running tomorrow, that might be good for the debugging standpoint, or Friday or something. Don't be putting it together for the first time on Monday. That's guaranteed to not work. Anyway, I decided to point that because this is due on Tuesday. Okay. So, I thought I would mention something in my continuing series of new things. This is an example of Microsoft trying to reinvent itself. How many people have seen the commercials? Yeah, they're very funny. The only thing so they have people staring at their phone and running into each other and a wide variety of other things. I love the byline. It's sort of, really? As somebody who's trying to actually interact with a person for real. Of course, the sad thing about that is there was a story I remember a few years ago about a 16-year-old girl who was texting on her phone and fell into a manhole and actually got rather seriously damaged, unfortunately, as a result. So this actually happens. But back to Windows Phone 7. I'm sure none of you text in a way that you would end up in a manhole. Yeah, okay, good. So word on the street, apparently, is that this is actually a very zippy interface. It's extremely responsive. Even folks like Engadget say that this thing may be more zippy than Android and the iPhone and stuff in terms of responsiveness, not necessarily the interface. Although people all like the interface for being simple. So I don't know yet. I haven't played with one. Has anybody played with one? What'd you think? Pretty nice? Yeah, so there's things that are missing. For instance, I think it doesn't have Flash yet, so the browsing experience is not that great yet. But it's got their attempt to go after games is Xbox Live. So the word on the street is that this is not as cool yet as the iPhone, but certainly cooler than a lot of the Android games. They've got music players that are pretty good. It's got Facebook integration, email, mobile Office, which of course everybody needs to do PowerPoint on their phone. Oh, and it actually makes phone calls too, but who cares about that anymore? One reviewer I was reading about this actually said, well, the one thing they're missing for an attempt at being a social networking phone is there's no Twitter. So apparently you can't tweet from this thing. I don't know. I guess that kills it for some people. But so it's kind of interesting. I've said this for a number of years now, and as is several other of us, that basically ubiquitous computing is the really cool frontier for computing. And what we're finally seeing with smartphones is we're really seeing that frontier come in, and we've seen new operating systems. This is a complete remake of the Windows mobile complete remake. It's not even, doesn't even run Windows mobile apps anymore. Android is a complete strip down of Linux with Java on top that's targeted at mobile. And once you've got kind of cloud in the background so that these things are basically getting services both locally and remotely, you start to get a really interesting system. We'll talk about distributed computing in the next few lectures. But you know, this is basically the network is the OS. I don't know if you've ever heard anybody say that. It's really true. Because these phones they do some cool things by themselves, but they're pretty brain dead without the network. Right? How many people have a smartphone? Okay, and how many people have gone in the BART tunnels on their way back and forth to San Francisco? And you know, what good is that? You know, huh? Yeah, so the tunnels are actually, that's true, are getting better. Okay, fine. Airplane, I don't know. So, good. So I'm glad to hear that somebody's actually played with it and think it's fun. I'm going to have to go to, apparently they're kind of hard to find. So basically Microsoft is pulling the let's make them artificially hard to get a hold of trick to make it seem like the demand is high. So I'll have to stop by my local Best Buy and see if there's one to play with. All right. So the other little aside I wanted to talk about is command queuing. So we did queuing theory a couple of lectures ago, and we also talked about how smart the modern disks are. Well, basically, disks do their own processing of requests, and they do it in their own order. So the ability to send a bunch of requests to a disk and have them process with the elevator algorithm implies a very important thing. It implies that you send more than one request before getting a response back. I hope that doesn't seem too obvious, right? So that means that these controllers are actually doing queuing by themselves. And this first showed up back in 1990, this ability to queue, but it's only kind of recently with some of the really big disks that this kind of command queuing has become very prevalent. And so, you know, you can't buy a 2 terabyte disk or a 1 terabyte disk without there being the command queuing on it. And, you know, basically the SATA 2 has what's called native command queuing. So if you look at a spec for a drive, you'll see, oh, what's NCQ? This is native command queuing. That means that you can queue up a bunch of requests, and the disk will reorder them and give you back the responses in whatever order it feels like it. Okay? And so if you look at a modern disk, this is still current, because Seagate hasn't come out with the next rev yet, but people are promising 2.5 and 3 terabyte drives sometime soon. But 2 terabytes, 720 RPMs, pretty standard, 3 gigabits per second. SATA 2 interface, 32 megabytes on disk, cache, etc. Yeah, question. It's native because it's in the disk as part of the actual controller interface to the disk. Yeah, so SCSI is an old standard for drive connections. SATA is a more recent one. It's called Serial ATA. And SATA 2 is actually the latest interface that has 3 gigabits and up to 6 in some instances. So it's the latest, fastest version. So if you buy a desktop or something, it's going to have SATA on it probably. Oh, a lot of things have changed. The formatting is completely different. I mean, you'd have to read the spec to see exactly what the details are. I mean, the essential idea of, in fact, the word NCQ is associated with SATA, not SCSI. But you look up the spec and you'd see, you know, it allows you to send requests in this way and defer them till later in that way and so on. Okay. All right. So let's take about a 5-minute break, or 4 minutes, and then we'll come back and talk about ILIDs, which is figuring out how to make things durable and so on. So let's continue. So let's close our laptops. So let's start talking about this durability question from earlier. And there's a series of words which I call the important ilities. And one of them, for instance, is availability, which is the probability that a system can accept and process requests. And oftentimes, availability is actually measured in nines. Okay, so for instance, a 99.9% probability that the thing is there when you're relative to when you need to use it, this is called 3 nines. Okay, and so the key idea here is some notion that failures are independent, and we're really saying, well, if I go to make a request, what's the probability I get an answer back? Now, availability, surprisingly, maybe the first time you hear this, doesn't necessarily mean you get a good answer back, just that you got an answer back. So availability is really about, is the service alive, not is it working properly? Okay, and all sorts of websites and other services are measured in nines of availability. Now, a different idea is durability. Now, durability is the ability of a system to recover even when there are faults, and usually it's applied specifically to data, and it doesn't necessarily mean availability. So a great example is the pyramids. Okay, so the messages written on the pyramids, meet me at 5 o'clock for dinner, were very durable for 2,000 years. Okay, that message was not getting lost. But it couldn't be read. So in some sense, that message, I made that one up. I don't think there's actually such a message on a pyramid. But messages of similar form were not actually available to anybody until they found the Rosetta Stone and were able to translate them and get them back. Okay, so does everybody see the distinction there? So the data was durable. It wasn't lost. It just wasn't accessible. Okay, now bringing this back into the domain of servers, you could say, well, my data is on some server that's super replicated and really works well, but it's down now, or the gateway's down and I can't get it. So the data's not available, but it is durable. Okay? Is everybody with me on that? So, and we might actually have slightly different techniques for availability and durability. Another one is reliability, and reliability is pretty much the metric that you probably all are most familiar with, or the way you think about things, which is basically the ability of a system to do what you were thought it was supposed to do. Okay, so this is the ability of a system, this is actually a quote, or component to perform its required functions under stated conditions for a specified period of time. This is the IEEE definition. It's usually stronger than simple availability, so it doesn't just mean you get an answer back, but you get a good answer. It includes things like availability, security, fault tolerance, durability, etc. Make sure the data survives system crashes and is available, and so on. So you might target availability or durability separately, or you might target reliability altogether. But in targeting reliability, you're probably going to have to deal with each of those components. Yes? The metric for a unit of reliability is, it's usually something to do with, mean time to failure. So MTVF is one metric. Okay. And actually, so durability, you might ask what the metric for durability is. When we used to talk in the OceanStor project, which perhaps I'll talk about at some point, about trying to save data for 1,000 years. Digital data lasts for a very long time, just like the pyramids. The problem with that notion is there's always some entropy in the system you can't suppress, and so data will get lost. There's some rate at which data is lost. And so we often talked about durability in terms of the fraction of the blocks lost per year. Okay, so that was kind of our fraction of data lost per year or whatever, and that was kind of our metric of durability. The lower that number, the better your data would last for a long time, because you could think of data as sort of shrinking in how much you can recover over time. All right, good. Questions? Other questions? Yes. You know, data loss is, so I'm not sure what you mean by nonlinear. I think of data loss actually kind of almost in a memoryless Poisson fashion. So if you take any given bit, there's some rate at which the bit is lost. And then when you add all those bits up, you're basically, your failure rate is kind of going as a function of the number of the bits. So it's linear in the size of your system. No, not necessarily. Because if what you really, so this is a great question. So the basic answer to this is, you know, view this from an entropy standpoint. Your bits, there's some rate at which they're decaying, and at some point they decay to a point at which you can't recover them. We are assuming long-term storage. Yes. Until the unfortunate event where all three of the replicas go. There's some probability of that, which would lead to a loss rate. I'm not saying that this fraction of blocks lost per year isn't in the 10 to the minus something number, which is very small, but it's there. And when you start worrying about data being preserved for 1,000 years, it turns out you start noticing these numbers. Good questions. Any other questions? It's amazing what conversation we can get with three words. So ilities are important. That's why I say important ilities. So let's talk about crashes now. I've been promising to talk about log-structured and journaled file systems. So the idea behind a log-structured or a journaled file system, and they're similar in a way I'll describe in a moment, is that all changes to the file system are treated as transactions. And what is a transaction? A transaction is something that either happens in its entirety or not at all. That's the important aspect of a transaction. And the idea here is that, for instance, if we're writing data to a file system or we're making a new directory or we're doing all that, we commit the data exactly once, okay, because we write it to the log first, and then once it's written to the log, we then work through the log and make sure it gets committed to the live file system. So what does that mean? That means that we're taking all of the things we're going to do and we're writing them out into the log first, which is this linear set of blocks on the disk, and then we work from the log to make changes to the file system. Because once things are in the log, then the system can crash as many times as they want. We can look back in the log and we can figure out what didn't get applied to the file system before it crashed. Okay, and the reason this gives us transaction semantics is we actually put a start transaction in the log, and then we going left to right, sorry, we start transaction in the log, then we write stuff to the log, and the last thing we do is we atomically write an end transaction mark. And if we reboot and we see there's no end transaction mark, we don't bother doing any of this at all. Okay, and therefore we get this clean semantic that either your data made it entirely there or not at all, and we never get this sort of half state. Okay, now you might say, well, but that doesn't help me because my data was written, but the transaction didn't make it and it didn't go on the disk. Well, the point of transaction systems is you'll be told when the transaction's committed, so you won't think the data is there until it says, yeah, your data is safe, and then you can trust that it is. Okay, so this is adding a level of confidence that the data is really there. Okay, now, go ahead, yes.
So, is the transaction that gets written to the log after the data's already there or before?
So basically the idea, so in its most extreme form, what you do is you write all the changes are written in a form that, you know, well, I'm going to make the following changes to the inodes. I'm going to alter this. I'm going to extend the file that way. Here's all the data I'm going to write. And then you say end transaction. And all of that data, this is the most extreme form of this, gets written to the log, and then you go and modify the file system. So the nice thing about it being in the log but not the file system, and the only reason that would happen is because we crashed, is that then we can go through, recover, and make the changes into the file system when we reboot.
So the system wouldn't say that your transaction's done until it's all in the file.
It actually would say your transaction's done the moment you are able to put the transaction committed into the log, because you know from that point on, it may need a reboot or something, but eventually it'll make it to the file system. Now, what you can see here is this most extreme form that I've just described to you seems like we're writing the data twice, right? Because we write it out to the log and then we write it to the file system. But in fact, in the most extreme form, that's exactly what you want to do, because that's the only way you can be sure that you get consistent changes to your file system. I know there's a question. Just hold a sec. And the reason that we do it that way is, if you think about a file system, all of these pointers, right? There's 12 or 10 single pointers, and the inodes look like this, and then they're built in this directory structure, and it's this complex complex tree of stuff. The log is this nice linear thing. So we say, here's all we're going to change. And then we start tweaking and changing and twisting and putting this thing into the file system. And once we've got it in the log, we know that we can complete that complex twisting and changing of the file system after the fact because we've got enough info in the log. Yeah, there was a question.
So how much faster would writing to a log be than
So the reason writing to the log is so there's two things about writing to the log. The reason it might be faster is because all the blocks in the log are guaranteed consecutive on the disk, because your log is some chunk of several tracks that are just made for that. Is it faster to write to the log than it would be to write to the original file system? Maybe not, but we're never in a state in which the file system is inconsistent, because we wait until we've committed everything to the log, and then we go and start tweaking all these pointers.
My question was, how much faster would it be? Like writing to a log and updating the file system?
So I think my answer was it might be faster because things are consecutive on the disk, but it might not be faster because you're writing twice. It's certainly likely to be slower than not having the log at all, but you gain this reliability factor. I don't know if I answered your question. Okay. Think about whether I answer it, and you could ask again. So what's the difference between a log-structured file system and a journaled file system? So log-structured file system is actually a particular type of file system in which the data is actually in the log. All right, now I'm not going to go into this in too much detail. You can ask me offline if you like, but imagine that, you remember that file structure with all of these pointers and so on? What happens in a log-structured file system is all the data goes into the log, and think of it as just spiraling its way into the disk. Right. And that is every write from every process to every file just goes in the log altogether, interleaved, And what we do is we adjust all of the pointers in the file system to point into the log. Okay, so the data is the log, or the log is the data, or whatever. The log is the file system. Okay, great write performance. Right, everything's sequential. Really bad read performance. Everything's not sequential, right? Because you got to pull it off of all these places. So typically in the log-structured file system, they actually have to have what they call a cleanup phase, which goes through and reorders all the blocks and puts them sequentially after the fact. The journal file system is more like what I was mentioning before of a log, which is there is a chunk of disk that's just reused over and over again that only represents the set of transactions that haven't been properly committed to the disk. Okay? And so basically, the log is used to asynchronously update the file system. When you've successfully done an update, you remove the entries, and then you could keep reusing things. And after a crash, you basically redo things that are in the logs that haven't made it to the file system. Okay. And examples, by the way, journaling is pretty common. The ext3 is a good example, XFS in Unix, and so on. Yes? ZFS journal, I think it might be, yes. Yes, question?
For something like server logs are very write-only in nature, why would you want to use a log-structured file system?
So, as opposed to a journal system, the idea behind the log-structured file system really was about making sure that writes were fast. And, and it was trying to combine, it's sort of the ultimate locality for things going to the disk that are new. And, it was proposed as a nice cross between speeding up writes and being reliable. And it's actually, I don't know that there are too many pure log structured systems anymore. Most of the systems are actually journaled. Okay. Good. You know, by the way, from a logging system, so the log structured file systems actually, you only write once, not twice. Right? So from that standpoint, it's certainly less write bandwidth to the disk. But it's got this unfortunate need to rearrange things later to get performance out of it. So I can point you to papers, by the way. This was originally some folks at MIT actually wrote the first paper on log structured file systems. Questions? So how else can we make file systems durable? Well, one thing that happens just because you buy a disk from a good manufacturer is that every piece of data that's put onto the disk is actually encoded in an error correction code. And these codes are what are called Reed-Solomon codes, and I'd be more than happy to talk. That's a whole another lecture that I usually reserve for my 252 class. But imagine that basically in addition to the data you're writing, you actually write some redundant bits that are mathematically related to what you write on the disk. And as a result, even if some of the bits fail, you can still recover the data because you've got enough extra bits. Okay? And Reed-Solomon codes show up everywhere. They're on CDs, they're on disks, and so on, and they're particularly efficient at the number of extra bits you need to handle the number of failures you get. Okay? Another option, oh yeah, go ahead, question. How many bits are actually bad? There's actually there's a fair amount of bad media, and part of the reason for that is the density. Remember, I think I mentioned the current density for a 2 terabyte drive is like 400 gigabits per square inch. It's a lot. Okay, so imagine with your little magnifying glass trying to look at all those bits. So it's defects in the media are prevalent, and if you didn't have some way of recovering from them, then the whole disk would be bad. And so then you say, well, how many disk blocks are bad? Well, it turns out that's much smaller because the error correction codes allows you to deal with slight imperfections. So that's one thing. So the second thing I should mention is, in addition to there being just surface imperfections on the disk, the fact that we've crammed so many bits together means that essentially they occasionally get a little intermixed in a way that the DSP algorithms can't extract, and so you'll lose a bit because 2 bits next to it are sort of interfering with the signal in some way that doesn't allow it to be recovered. So you can actually end up with soft errors pretty easily on this as well. Things that when you rewrite the block, they would go away. Yeah? So this is totally handled by the hard drive. So this is in the hard drive firmware, does Reed-Solomon codes. So in fact, the OS never has to deal with this. The only thing the OS would ever have to deal with is if a block is so bad that the ECC codes don't work. Question, yes?
Well, I mean, there are 2 cases, right? There's one is completely mangled that you think is real data, and then you'd have to do some recovery. But the other one is detection, where you can't recover it, but you might signal the operating system that you detect the problem, in which case you might want to do something else.
Yeah, so there was something that was brought up here. So one of the points that is true is with any error correction code, there are errors that are undetectable to the error correction code where you think it's actually correct. Can't do anything about those, but fortunately they're extremely low probability events. The second thing to note is whenever you get an error, a block read error off of a disk, the operating system, one of the first things it'll do is try the read again, because oftentimes it can get it the second time through. So, okay. Error correction codes, by the way, are a completely interesting topic that it's a lot of fun to talk about, and I give whole lectures on that. The other thing we can do, this is a different type of reliability, durability thing, is we could completely eliminate delayed writes. Obviously, we make sure everything's pushed to disk. We could put logs everywhere. Or what we could do is we could use NVRAM, so non-volatile RAM, or flash, or phase change memory, or any of those, to make sure that all of our data is pushed out to this type of RAM quickly, and therefore it will survive reboots before we try to put it on disk. And unlike the logging case I just told you about, this one's fast. So we can basically take our data, push it to the NVRAM, and then get it to the file system, and we'll survive a reboot at that point. Okay, so just by having some non-volatile RAM, we can make our reliability process faster. And of course, as you can imagine, we could put the log in the NVRAM as well. Okay, and by the way, why do I call this NVRAM? It turns out there are chips you can buy. They're just like DRAM chips, but they've got a little lithium battery on them. And so they're non-volatile as a result. Okay, and will survive some amount of time without power. Otherwise, flash and PCM are also becoming very common. Okay. Now, the problem with all of these techniques is these make sure that the data survives locally. So how do you make sure the data survives in the truly long term? Well, this is all about replication. So if you notice, ECC is actually a form of replication. We're putting redundant data into the system. So the important element for all of these is that the failures are independent. So take your Google example. I don't remember who brought up the Google file system, but you got 3 copies. The assumption there is that only one of them is going to fail at a time. On the other hand, if, say, one of the Google sites got nuked, that was what I meant to say, you probably lose your data because all 3 copies are gone. Okay, that's the worst possible non-independent failure. So, so we could put copies on one disk, which I don't know if any of you, I use copies when I'm hacking sometimes. You check into SVN multiple times so that when you start noticing the thing isn't working anymore, then you back out your last copy and go to bed, right? So that's one use of SVN, which I don't suggest to you guys. But the problem is if the disk fails, you're toast, so you can put copies on different disks. But if the server fails, you're toast. You could put copies on different servers, but if the machine room, if the building's struck by lightning, you could put copies on different servers in different countries. Okay? You could put copies on the moon, I suppose, right? There have been experiments that reflect laser power off the moon. I suppose you could actually have an optical link to a backed up system on the moon. I don't know that any of that exists yet. Or if it does and you find out about it, you're probably going to disappear. So now we'll talk about these distributed system things in a couple of lectures, but I did want to finish off with one idea, which is RAID. So how many people have heard of RAID before? So this is a 4-letter acronym from Patterson, just like RISC and a whole bunch of other. He's very good at 4-letter acronyms. Redundant arrays of inexpensive disks. And the idea here is that the data is stored redundantly on multiple disks, and this is really targeting kind of a middle area here, which is failure of one disk. Okay? And so here, RAID 1, or mirroring, is the simplest idea. And the idea here is you never just write to one drive, you write to 2 drives. Okay? And the reason this is great is, well, when one drive fails, you still got a drive with all your data on it. Okay? So each disk is fully duplicated onto its shadow. What's kind of nice is you get really high I/O rate on the read side because you've got 2 identical copies. You can have 2 different reads going on, both at the full bandwidth, right? And this is the most expensive of the RAID solutions because you've got 100% overhead. However, I never buy a desktop anymore without RAID 1. Okay, disks are cheap enough, and you go to Dell or whatever, and when you order it, you say, I want RAID 1, and I just want to put in twice the number of disks as what I really want. So if I want I want a terabyte of storage, I put in 2 1-terabyte drives. And RAID 1 is built into most low-end desktops these days. And this saved me once because I had a brand new machine that was 3 months in, and one of the drives failed. And it was under contract. The guy came out, put in a new drive, and I didn't lose any data. In fact, I hardly noticed. Okay? So obviously, relative to the 2 drives, we've got a little bandwidth sacrificed on write because we have to make sure that, well, for one thing, we got half the bandwidth we'd have with 2 separate drives, but also typically there's some synchronization that goes on to make sure that we are writing together in parallel. The reads are optimized. And the recovery here is simple. disk failure, you replace the disk, and the system copies from one disk to the new disk, and when you finally have duplicates in the new disk, you're back up to full redundancy and you're good to go. Okay? Everybody with me? Now, why is this called RAID 1? Yes. Now, you guys are going to try to come up with a logical reason for this. There isn't one. So as I understand it, Patterson had about 5 or 6 different, actually 5 at the time, different RAID algorithms that he was talking about. And so they were writing a paper, and they said RAID 1, RAID 2, RAID 3, RAID 4, RAID 5. And unfortunately, so RAID 1 survived. RAID 5 is this other one, which I'll close with. But the idea here is that now we have more than 2 disks. So here's a case of 5 disks. So each column here is a disk. And what we do is we take the 4 blocks on one disk, or we take 4 blocks, we XOR them together, and we get the 5th disk. Okay? And so we think of these as a stripe unit. So here I have 5 disks, so I have 4 data disks and 1 parity disk. Okay? And clearly this has increased bandwidth over a single disk. And notice that this means XOR, so D0 XOR D1 XOR D2 XOR D3 is blocks, every bit XORed together in parallel. And the reason this is useful is because I can destroy any one of these 5 disks and I can get back its contents just by XORing the other 4. Okay, so this particular technology is completely resilient to one disk failure. Okay, so if D3 fails, then D3's data is D0 XOR D1 XOR D2 XOR D0. Yeah, question? So the reason we move the parities around, we'll talk about something like RAID across the globe later, but the reason we move the parities around is actually it turns out the parities are a hotspot. Because if you think about already having data on here, suppose I want to modify part of D3, I've actually got to read P0, recompute what I'm changing, and then write back P0 as well as D3. And so by rotating them around, we make sure that nobody's a hotspot. Okay. We're going to talk about this, I think, in section a little bit too. But let's conclude here. So we talked about ILIDs today, availability, durability, reliability. We talked about how to use a log to improve reliability. We actually talked about RAID. And next time, we're going to talk about authorization, and we're going to dive into networking. So have a great weekend. Good luck on your project.
Patterson have an acronym that didn't get